So we're continuing to talk about graph coloring. I want to talk about edge coloring for most of this lecture, but I'll start by just mentioning a few more things about coloring vertices. So some famous graph coloring theorems, which we won't prove. So probably the most famous, you may have heard of this, the four-color theorem. Which says that if G is a planar graph, planar graph is just a graph that can be drawn on a plane, on the chalkboard, without crossing any edges. So planar graph just means can be drawn in R2 without crossing edges. So then the chromatic number of G is at most 4. Okay, so unfortunately we won't be proving this because there doesn't even exist. So this was proved in the 1970s, I think. But to this day, nobody has like a reasonable proof that can be explained to a human, essentially. So the proof relies on computer computations, like thousands and thousands, way too much computer computation. But yeah. But essentially, it is just like a basic induction proof. But not really possible to lecture it. So graph coloring is a huge topic. There's so many interesting theorems. I'll just maybe name or mention one more. Because I think this is kind of so last time we saw perfect graphs, which are graphs where the chromatic number is equal to the clique number, and that happens for all of its induced subgraphs. From that, you might get the impression that to have a high chromatic number, you need to have like a big clique or some kind of dense substructure or something. But I want to kind of explain to you that this is actually very false. So you could have chromatic number 1000, but no small, dense substructures. So this is a famous theorem, but first I need a definition. So the girth of a graph G is the length of the shortest cycle. In G, and a famous theorem of Erdős says, so for any, let's say K at least 2 and G at least 3, there exists a graph G with chromatic number at least K and girth at least G. So with chromatic number at least K and girth at least G. Okay. So not only does this graph not have, so like let's say the chromatic number is at least 1000. Like, okay, one way you could have chromatic number at least 1000 is to have a clique of size 1000, right? But this says that not only do you not have to have a clique of size 1000, you don't even have to have a triangle, right? It could have no triangles at all. And in fact, it could have no triangles, no 4 cycles, no 5 cycles, no 6 cycles, no, the chromatic number could be 1,000 and the girth could be 1,000,000. So there's no cycles of length, at most 1,000,000. Okay, so like somehow having high chromatic number is this very strange property that kind of, it doesn't depend on some small, dense kind of cluster of vertices. It just depends on the structure of the graph kind of globally all over the place. And it's kind of hard to understand. Okay, we're also not proving this, but this is just like for kind of context, I guess. Okay. Any questions about either of these theorems? Okay. Next time we will prove something related to the color theorem. Okay, so let's talk about edge coloring. Okay, so a function f from the edges of a graph G to a set C, let's say C is a set of colors, is proper if there does not exist two edges of the same color. So let's say two edges E and E prime, well, which are different edges, such that f of E, which is the color of E, equals the color of E prime, and E and E prime share an endpoint. Okay. All right, so in a proper edge coloring, if I look at the edges coming out of a vertex, they should all have different colors. Okay. So you're not allowed, that, right? Okay. In other words, if you look at the edges of a given color, they make a matching, right? So in other words, it's a decomposition of the edges into matchings. So so similar to vertex coloring, where every set of a given, so for any color, the set of vertices of that color is a stable set. Now the edges of a given color form a matching, right? Okay, and then we can define the chromatic index. So last time we had chromatic number, now we have chromatic index. Chi prime of G is the minimum number of colors in a proper edge coloring of G. just like with a lot of things in this course, a nice place to start is with thinking about bipartite graphs. So there's a kind of another theorem of Koenig. So Koenig's edge coloring theorem. Which says that for any bipartite graph G, the chromatic index is equal to the maximum degree of G. And now that I write this, I don't remember if we ever defined that, but in case we didn't, delta of G, capital delta of G is the maximum degree of a vertex in G. Okay, so the maximum number of edges incident to any given, to a vertex, right? Okay. So actually, this is something that you'll prove on the 4th assignment, I think. But by the way, so is the statement clear? Or okay. I'll maybe just say a quick sort of rough proof, but and I should say also the proof that you give on the assignment is different than the one I'm going to tell you now, because I specify how I want you to prove it basically on the assignment, and it is a bit different. But here's like a quick idea of how to prove this. So maybe a proof sketch. Okay, and I think this is good enough to get all of the details. So you could kind of fill in the steps or the blank, or fill in the gaps kind of on your own. So so the first step I would say is observe that any graph G is a subgraph, or sorry, any bipartite graph G. So G is a subgraph of a delta G regular bipartite graph. Okay, so assuming G is bipartite, I can find a supergraph of G, like a bigger graph, which is actually regular. So regular means every vertex has the same degree, right? I think a natural way to do this is although this isn't really going to work. So let's say your maximum degree is 3 or something, and I've got this vertex of degree 2. You might think, okay, well, let's find another vertex over here of small degree, like let's say degree 2, and add edges or something. Doesn't actually work really, but there's a cheaper way of doing this. So here's how I would do this. So take your graph G, and actually there's something related to what I'm doing right now, which is kind of useful on assignment 3. It's related but slightly different. But anyways, take your graph G, right? Take 2 copies of it. And then if I have a vertex which has degree less than capital delta, so let's say this vertex here, let's call it W, has degree less than delta of G. Well, what I could do is, for all such vertices, I could join it to its sort of twin in the other copy, and do that for all of them, right? So if this one has small degree, I join it to its twin up here. And this stays bipartite because if I just think of two coloring it, like so if I color this red on the left side, blue on this side, and then I make this blue and red, I switch the colors on the two copies, it's still going to be bipartite. And now what I've done is I've anyone who had degree delta still has degree delta. And anyone who didn't have degree delta, their degree's gone up by 1. Because, yeah, they've got this extra edge, right? But then you could do it again, right? Double this whole thing, and then join things that have degree less than delta to their kind of clone over there. And then you get a delta regular graph eventually. Is that procedure clear enough? So it might be a way bigger graph, but yeah. Yeah, so this has all of the edges of G before, and then, yeah, I join things between the copies to sort of boost up the degrees of anyone who had too small degree. Okay, and this graph, at the end, because you're going to duplicate this again, possibly, at the end it might be way bigger than G, but it contains G as a subgraph for sure. Okay, step 2. So actually what we're going to do is color, there's one, okay, I'm kind of jumping ahead here. Can anyone see why this is kind of, so I'm kind of jumping ahead to proving the upper bound over there, but the lower bound is kind of the easy part. They all have to be different, so you have to use at least that many colors. So yeah, so this is kind of the easy part, and what I'm doing is the harder part. So yeah, that's for any graph G. So step 2. So now actually we just take this. Basically, the first step tells us that we can assume the graph is regular. I'll just color the regular graph that contains it. So if you use Hall's theorem, any, let's say, k-regular bipartite graph for k at least 1 has a perfect matching. So that's not what Hall's theorem says, but it's an easy application of Hall's theorem to prove this. I mean, the proof is basically, let's say I've got my x and y, take a set here. If it doesn't have a perfect matching, by Hall's theorem, there's a set who's got a smaller neighborhood. Than S. But each vertex here sends k edges to the neighborhood. But then by pigeonhole, there'd be a vertex in the neighborhood with degree bigger than k. Because the neighborhood's smaller, there's k times size of S edges going that way. There would have to be at least that many edges going this way, but then the number of edges per vertex is larger. So there'd be a vertex of higher degree. Okay, and so basically then, if this thing has a perfect matching, take those edges of the perfect matching, give them color red, delete them. Now I get a k-1 regular bipartite graph. It has a perfect matching. Color those blue, delete them. It has a perfect matching. Because every time you delete a perfect matching from a regular bipartite graph, it just becomes regular with a smaller degree, right? So kind of pull out these matchings one by one. So and get, so the perfect matchings. And then if I look at the copy of G inside of this thing, it gives me, so we get a coloring of G with delta of G colors. I should say, I guess, an edge coloring, proper edge coloring. Okay. So yeah, this was meant to be a little bit sketchy, but is the sort of idea clear? Okay. And yeah, you guys will give, I guess, with hopefully a less sketchy proof on the fourth assignment. Okay. There's actually a really nice connection between this theorem and what we did last time for perfect graphs. So to explain that connection, I need something called the line graph of a graph. So the line graph of G, so denoted L of G is the graph with vertex set E of G where two vertices of L of G are adjacent correspond to edges of G that share an endpoint. So I don't know if I can come up with a good example, but that's my graph G. Then I'll have a vertex for each edge. So I've got a vertex corresponding to like the edge AB, then the edge BC, CD, DA, and a vertex corresponding to BD. These are adjacent because they share the vertex B. These ones share the vertex C, the vertex D, and these share the vertex A. And this one would be adjacent to all of the other ones, I guess. Yeah, because these two share B, they share D, and they share D. Right, so this would be L of G. Okay. So can anyone see like the connection between the chromatic index of G and the chromatic number of the line graph? Like basically coloring the edges of G is the same thing as coloring the vertices of L of G, right? So yeah, an observation is that the chromatic index of G is the same thing as the chromatic number of the line graph. Okay, so I was trying to say that this has some connection to perfect graphs. I guess let's say that, well, okay, maybe I'll just say this in general. Like, any guess for what like the clique number of the line graph is? Pretty much always, except there's like one weird case, but like basically it's a max degree, right? Because, well, the edges coming from one vertex, that'll make a clique, right? So yeah, it is the max degree. Kind of, I think, unless, and there's one stupid case, unless G is a triangle. It turns out that then omega of L of G will be 3, and the max degree is actually 2. But other than this one case, I think it's always the max degree. This one's kind of annoying because it's like all three of these edges intersect, but they don't intersect at one vertex. But yeah, beyond that, it should be, well, okay. I guess it could be this graph G or like some stupid thing like with some isolated vertices or whatever, but let's not worry about that. Essentially, it's this. Especially, so if G is bipartite, then it's definitely this. But wait, this thing is the chromatic number of the line graph. That thing is the clique number of the line graph. So there's this thing that the chromatic number of the line, if G is bipartite, the chromatic number of the line graph of G equals the clique number of the line graph of G, right? So this is, and the same thing holds for every induced subgraph of the line graph. Because what is an induced subgraph of the line graph? It's the line graph of a subgraph of G. Because it's like, take some edges of G and make a line graph based on those edges, which is a subgraph of, and so anyway, if you kind of put this all together, so a corollary of this theorem is that if G is bipartite, then the line graph of G is perfect. Okay. But actually, so remember we were coming up with examples of classes of perfect graphs. This is a new one. This was not in the list last time. We didn't list this one as a perfect, but yeah, line graphs of bipartite graphs is another class of perfect graphs. And then by the weak perfect graph theorem, that means that also the complement of the line graph of a bipartite graph is perfect. Okay. So I'm not going to go further in this direction, but maybe it's worth pondering. I wonder if that connects to anything else in the course. So something we've seen. This is a hint for assignment 4. Okay, and I won't say anything more about that, I guess. This will also be on YouTube, so. But any questions about any of these things? Okay. Yeah, I see what you mean, but I think, isn't it usually that you, instead of replacing the lines by points, isn't it, well, maybe it depends on the problem, but if you have some kind of regions or something, often you replace the regions by points or something. Well, okay, it depends on what, maybe, oh.
I remember the like it has something to do with like for geometry when you have like that.
Okay, yeah, so you can, yeah, I guess I was thinking of the wrong thing, but if you, yeah, often it's for projective planes and things like that, for example, it's good to think of them as a bipartite graph where you got points and lines, and like there's an edge if that point is on that line, and then you can kind of like do some kind of duality between the two. Yeah, no, that is, yeah. That might actually be kind of related to taking line graphs or something. I'm not entirely sure, but yeah. Okay, so this is this is kind of the key theorem if you're talking about coloring the edges of a bipartite graph. We just know what the answer is. So actually, like it's kind of interesting. Like this problem, you might think the natural certificate, like if you wanted to have a certificate that the edge chromatic number is at most 10, you'd have a coloring, right? But you could also just say, oh, let's just check that all the degrees are at most 10, and that also implies the edge chromatic number is at most 10, or the chromatic index. Anyway, so let's talk about more general graphs, not just bipartite. So unfortunately, it's not so simple for general graphs, but it's almost as simple. So there's this theorem called Vissing's theorem, which says for any graph G, well, so we still have the trivial lower bound that the chromatic index is at least delta of G. And now what we're going to prove is an upper bound that it's at most delta of G plus 1. So like for bipartite graphs, we interpreted this thing being equal to delta as being like, it's like a perfect graph, like the line graph is perfect. What this is saying is that actually for any graph, okay, the line graph's not perfect, but it's like kind of close. It's like, it's either equal to that or plus 1, right? It's pretty close. You might actually think that, okay, so this thing can only be two values, this number or this number. There's only two possible values. Like, it couldn't possibly be that hard to determine which value it is. But actually, it is very hard to determine this. So kind of a sort of side note, so determining, the decision problem asking whether the chromatic index is equal to delta of G, unfortunately is NP complete. So kind of weirdly, even though we can narrow this down, almost get the answer, to actually get the actual answer is a hard problem. Okay, so for this, like your input would be a graph, and the question would ask, is it true that that this equals that? And yeah, that's an NP hard or an NP complete problem. Okay. Okay, but to color it with delta plus 1 colors is not actually, we can't do that. Okay. Okay, so the lower bound is easy. We've already seen that. So because just look at the edges incident to the maximum degree vertex. So we prove the upper bound by induction on the number of edges. Okay. I mean, you need some kind of, to do induction, you need a basis case, but I guess basis case, I don't know. Well, this is kind of trivial. I can easily color the empty set with most one color, just actually use no colors. So, okay, so really it's like the inductive step that's interesting. Okay, so take any edge E of G and delete it. Okay, and by induction, well, so if I take away an edge, the maximum degree doesn't go up. Okay. And so the new graph can be colored with delta of G plus 1 colors. So we can color G minus E, so I mean color the edges of it with delta of G plus 1 colors by induction. Okay, and somehow we want to, so basically everything is colored. All of the edges are colored, just not this edge E, right? We put back the edge E and it doesn't have a color, right? So we need to figure out a way of coloring the edge E, basically. Okay, so label the endpoints of E so I'll call one endpoint V and the other one Y1, and just do it arbitrarily. Okay. Okay, so I think the best way of describing this proof is basically with a picture with some words added. So I've got V, and I've got Y1, right? And that's my uncolored edge. Okay, so let's say white means there's no color, and we need to give it a color somehow. So the total number of colors is the maximum degree plus 1. So that means at every vertex, if I look at a given, let's say vertex U, and the edges coming out of it, like there's always some color that isn't on the edges coming out of U, because there's delta plus 1 colors in total. So observe that every vertex, let's say U, has so we can call this like a free color. And what I mean by free is that it's not used on any edge from U. Okay. So not used on the edges that contain U. Okay. And actually, if you think about it, V actually has two free colors because, like, there's one edge that's not colored. So anyway, but it doesn't actually matter that there's two free colors, but let's just pick a free color for V. So, like let purple, I don't have a red chalk. I would have picked red probably, but I've got a purple chalk. So let purple be free for V. Now, one obvious thing is if purple is free for Y1, I just give it purple and we're done. We can go home, right? So obviously we cannot assume we're that lucky. So probably Y1 has some purple edge touching it. Otherwise, yeah, I would just give that purple. Y1 has some purple edge touching it, but there's some color that's free for Y1. So let's call that yellow. Ooh. Okay. So let yellow be free for Y1. Okay. So what I'm going to do is I'm going to start at Y1. I'll follow the purple edge that touches Y1. And then if there's a yellow edge coming from this vertex, I'll follow the yellow one. So I'll just do an alternating walk. I follow a purple edge and then a yellow one. And if there's a purple edge, I follow it. There's always going to be only one purple edge, right? Because it's a proper coloring. There's not two choices. So we just keep alternating purple, yellow until it stops. So let's say W1 is a walk that alternates purple to yellow. So starting at Y1, and alternating purple, well, maybe basically purple, yellow, for as long as possible. Okay. So the first edge will be purple, and then, yeah, if this one doesn't have a yellow edge, then I stop. If it does have a yellow edge, I follow it. If that one doesn't have purple, I stop. If it does, I follow it, and etc. Okay. So one thing I claim is that this walk is quite simple in the sense that this walk isn't going to come in and re-intersect itself. Like it's not going to do things like this. Can anyone see why? Or even like intersect itself and then continue on and then come back off. It's not going to do things like that. Can you see why it can't possibly intersect itself? Yeah. No matter what, like if this was purple and this was yellow, right? And then like, what is the color of this one that comes in? It's either purple or yellow, and it would have two of the same, right? So this is actually quite a simple kind of walk. It doesn't intersect itself. And in particular, it's got a finite length, right? Now let's suppose that it ends somewhere that's not V. So suppose it ends at some W. If it did, I win. Because what I would do is just switch all the edges on that walk from purple to yellow or yellow to purple. Right? So imagine this one goes yellow, purple, yellow, purple, yellow, which is allowed because why did I stop here? I stopped here because there's no yellow one coming out of that one. Otherwise, I would have kept going, right? So if this one ends up being yellow, that's not a violation here. And so if I could switch them, then I'd make this one purple, and then we win. So if W1, the walk, doesn't end at V, so it's a bit different if it ends at V. We'll see that in a second. Swap the edges, swap the colors on the walk. And then color VY1 with purple. Okay, so it does, so yeah, so it must end at V. But if the walk ends at V, I know what the last color was. It wasn't purple. Purple is supposed to be free at V. So the last color was yellow. Okay. Okay, so anyway, so W1 ends at V with a yellow edge. Okay. Actually, at this point, there's not much and actually maybe for the sake of this picture, I want to draw this a bit differently, but okay. So yeah, so at this point I haven't won. I need to do something else. So what I'm going to do is, if this happens, I take the second last vertex on the walk, I call it Y2. Okay. And now what I'm going to do is shift. I'm going to take this yellow edge here, uncolor it. So this one goes from yellow to no color, and this one is going to get yellow. So I remove the color here. And once I've removed that yellow thing, now V doesn't have any yellow edges touching it, because it only had one, right? Because it was a proper coloring. So now I'm free to make this yellow. Because yellow is free at both. Once I uncolor both of these edges, yellow is free at both of them. I can make that yellow. And now, okay, now I'm back to this. Now I've got a new vertex Y2, and I'm actually going to play the same game. So I observe that purple is free at V again, right? So I mean, basically the coloring at V is the same, except that one used to be yellow, and now that one's yellow. So purple is free at V. And then there's some color that's free at Y2, which is not purple. It's some, because I mean, I can see the purple edge. So it's something else, right? And what I would do is then kind of, well, I would follow the purple edge, and then let's say blue is free here, then I follow blue edge, purple, blue, so on and so forth, until I come back to V, and then I kind of do this again. So let's just describe maybe the general situation. So in general, suppose, Y1 up to YK are neighbors of B. Okay. So this is this picture shows you what it looks like when k equals 2, right? This is kind of, again, I'll describe a sort of general situation that you'll be in as this algorithm proceeds. So, and let's say P1 up to Pk minus 1 are paths in G such that so my path P1 in this picture would be the path that starts at V and follows this alternating thing until it goes to Y2. Let me remember what properties I need. So the edges Vy1 up to V, Yk minus 1 have distinct colors. The edge Vyk is uncolored. Okay. So if k is 2, like that's so far describes the situation here. This edge is not colored. That has a color. And for each j between 1 and k minus 1, Pj is a path from V to Yj plus 1 that alternates, alternating between purple, the special color we picked at the beginning, and the color of Vyj, this particular edge. Oh, and also purple is free at V. Okay, so this kind of explains how to get to, like what happens when k is 2, but more generally, the picture is going to look like this. I need to not completely run out of colors here. Can you see the difference between this beige and this yellow? Okay. Okay, so let's say, this would be like kind of the case k equals 4. And yeah, basically there's some kind of a so my path P1 would be starting at V, go to Y1, follow this yellow-purple thing until I get to Y2. That's the thing we constructed before. And then there would be some kind of a blue-purple path that brings me to Y3. And then there'd be some beige and purple path that brings me to y4. Okay. Okay. So yeah, after some number of steps, this is what we end up with. Now again, I'm going to look at this edge and say, I want to make this edge, oh, sorry, I think the last edge of this has to be purple. Yeah. Okay. So again, I look at this situation, I say I want to make that edge purple. Okay? I can't because that thing's got a purple edge coming from it. But y4 has a free color. So I want to say that basically if I can't find a coloring, I can keep repeating this process forever. But that's nonsense because it has finitely many. Repeating forever. So what I want to show is that basically if I cannot find a coloring at this point, I can extend to another like y5. And then where I'm in the same situation as I was before, except with more neighbors. And then that can't go on forever. Okay, so maybe I'll just show it in this example. And then basically, though, it kind of, in general, it works the same way. So let green be free at y4. Okay. Actually, maybe let's think of this sort of in two steps. So sorry, but so consider the color that's free. So some color is free at y4, right? If it's one of the colors we've already seen, so if it is one of the colors of one of the edges v, y1, v, y3. So let's suppose it's, for example, yellow. Then we're going to be happy because, so again, we do the same thing we did before. We take an alternating path, an alternating walk from y4. The first edge is going to be purple. The next one's going to be yellow, then purple, then yellow, blah, 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 right? So let's say yellow is free here. So I take a purple edge, I take a yellow, I take a purple, I take a yellow. Again, if this ends somewhere other than V, I can swap all the colors on that walk, and now purple will be free for y4, and I can color that edge with purple, and I'm done. So this walk has to end at V, but there's only one way that it could happen. It would have to go through this yellow edge because there's no purple edges coming to V. But that can't happen because similar reason we saw before, like if I have some kind of alternating purple-yellow walk, if it's going to use this edge, there's some first time when it intersects this path from y2 to y3. But the first time it intersects that path, it would create like, for example, two purple edges incident to a vertex or two yellow edges incident to a vertex, right? Because this walk has the same color pattern as this one. Okay, so yeah, if this color has been seen before on one of these edges, then the walk that you get by starting at y4 and at V. Okay, so it's a new color. Okay, so then, yeah, well, maybe I'll just say then we win by the explanation I gave there. So it isn't one of those colors. Let it be green. Okay, so again, we follow an alternating path, starting with Y4, going green, purple, etc. If it ends somewhere else other than V, I swap the colors on that path and I win. So it ends at V. And the last edge is green, because it can't be purple, because purple's free at V. Okay, so then, but now I claim that I can extend this to get a Y5. How do I do it? That's Y5. Take off that color. So make that one white. Make this one green, which is legal because green was free here. And now I've just extended and found another neighbor of V. And if you look at it, all of these properties will be preserved. That all of these colors are different. This edge is uncolored. I've got a path pj from V to, this green purple path goes from here to here, etc. So basically, now the argument says, okay, either this should terminate at some point and I get a proper coloring, or I can keep finding neighbors of V forever, but that's not possible. There are finitely many neighbors, so then we win. Okay. So maybe I'll call that a proof. This proof always ends up being more complicated when you have to write it out, but it's kind of a basic idea. Okay. Any questions about that? And by the way, you could turn this into an algorithm, right? I'm not sure what the running time is, but it's not going to be too bad. Okay. So I'm just going to end with like a couple of definitions that we're going to use next time. So next time we're going to talk about something called list coloring. So let G be a graph. And for each vertex V, let L of V be a list of colors. So to be clear, different vertices can have different lists. Okay. The idea in list coloring is that different vertices have different colors available to them. Each vertex has to pick a color from their personal list, and you have to have a proper coloring. So an L coloring, so where L is this kind of list, color list kind of function, of G is a proper coloring F such that F of V is in L of V for all vertices V. Okay. So this leads us to like a different type of a chromatic number called the list chromatic number. So the list chromatic number of G, which is denoted chi sub L of G, is the minimum K such that G has an L coloring whenever, so for every list assignment L such that every vertex has a list of at least K colors. Okay. It's kind of a, maybe at first it seems like a weird concept that like I'm giving different vertices different lists. Like, actually like the total number of colors in the universe is going to be larger if you do that, right? If I give different vertices different lists, there's more colors available kind of overall, right? If they have small intersection, which seems like that should make it easier to color. Like let's suppose every vertex has a list of size 2, but there's actually, if the union of the list has 100 colors, it kind of seems easier to color the graph, but it's not. So maybe an example, take this graph. So obviously the chromatic number of this graph is 2. It's bipartite. However, suppose I assign lists of size 2 in this way. So this vertex has to get color 1 or 2. That one has to get 1 or 3. I'm trying to find a proper coloring where, yeah, that one gets 1 or 2, that one's 1 or 3, 2 or 3, and then it's kind of the same on the other side. It doesn't exist. You could probably convince yourself of that, like, okay, without loss of generality, let's say I give this one color 1. That kills color 1 from these lists, right? Because if that one gets color 1, these ones can't, they're adjacent. But then that one gets 2 and that one gets 3, and that kills this vertex. So here the list chromatic number is at least 3. Okay, so generally these are different things. But next time what we're going to show is, well, okay, if you kind of color the edges instead of vertices, we're going to show that the list chromatic index of G is equal to delta of G for any bipartite graph, which is kind of a strengthening of Koenig's edge coloring theorem. And list chromatic number of G is at most 5 for any planar graph. Okay, so that's next time. All right, see you on Thursday.